All right, hello everyone. Welcome to week 4 of our Intro to Analysis series. In this video, I'm going to be talking about sequences. We're going to talk about the proof of convergence and divergence of specific sequences. We're going to talk about limit laws, and then we're going to talk about boundedness. So this is a super important lecture that we're going to get into. So let's go ahead and begin. Okay. So the first thing we need to do is define a sequence. All right, so a sequence of real numbers is just a function from the natural numbers into the real numbers. Okay, so we take in a natural number and we spit out a real number. Okay, so a sequence is, a sequence is just a list of numbers. It's another way we can think of it. So like here's a sequence right here. This is an infinite sequence. And you know, we can say, okay, well, this guy is the first term in our sequence, this guy is the second term in our sequence, this guy is the third term, and so forth and so forth. So we can see that we're taking in a natural number, and we're outputting a real number. We're taking in a natural number, we're outputting a real number, etc., etc. Okay, so that's what a sequence is. So some common ways to describe a sequence. For most of the lecture, I'm going to omit these parentheses, but just in case you see this notation in the book, Cummings uses the parentheses to describe sequences quite a bit, but I'm usually going to omit the parentheses. So like if I saw this sequence in a book, I would probably just write it as this. But yeah. Okay, so this is one way to write it. We have first term is 1, second term is 1/2, etc., etc. And in general, we can generalize a rule for the sequence. We can say that the function a sub n is actually going to be 1 over n, depending on what spot we're at. So when n is 1, 1 over 1 is 1. When n is 2, 1 over 2 gives us our second term, and so forth. So this is the rule of the sequence. We could also write an infinite sequence. I mean, usually people... I don't know that people really write this that often, but it's in the book, so I'll share it. They have the rule 1 plus n over n, and we're starting from n equals 1 to n equals infinity. So the infinity just means that it's an infinite sequence, and if you start at 1, you plug in 1 anywhere you see an n. 1 plus 1 over 1 gives you 2. Okay, now we go to n equals 2. 1 plus 2 over 2 equals 3 over 2, and so forth, okay? So that's how you do that. We could have a sub n, where the rule is 2 to the n, and so if you wanted to write these terms in the sequence explicitly, you would just say, okay, well, n equals 1 first. That's the first natural number. So for n equals 1, a sub 1 equals 2. For n equals 2, a sub 2 equals 2 to the 2, which is 4. A sub 3 equals 2 to the 3, which is 8, and so forth. So this is how you would write the terms in your sequence, and you can omit the a sub stuff and just write 2, 4, 8. Next one would be 16, etc. So that's our infinite sequence there. We could have something called a recursive sequence, where the next term depends on the previous term. So if x sub n is our sequence, x sub 1 equals 2, then the next term is going to be x sub n plus 1 over 2. Oh, actually, I think I meant to say minus 1 here, not plus 1. Okay, so if x sub 1 is 2, then x sub 1 plus 1 is x sub 2. Following this rule, it's going to give me, this is going to be x sub 1 minus 1 over 2. So, recursively defined sequence, x sub 1 was 2, so 2 minus 1 over 2 is 1/2. And therefore x sub 2 is 1/2, and you could find x sub 3 by doing the same kind of thing. Okay, so that's a recursive sequence. Okay, and I think no, I guess we didn't do this one. But yeah, so here's the rule. And if we want to just list out the elements, we would start at n equals 1. So 2 to the 1 minus 1 is just 1. 2 to the 0. 2 to the 2 minus 1 is 2, etc. 3 minus 1 is 4, etc. So that's how you would write this in that notation. Okay, and if we want to determine a specific formula for the sequence, I mean, there's a few ways to do this, but, maybe pause the video and think if you can come up with a rule here. But the rule for this specific sequence is a sub n equals n squared plus 2. Right, because of how the list is, this is a sub 1, this is a sub 2, a sub 3, a sub 4, a sub 5. And so if you put each of these natural numbers into the rule, so a sub 1 is 1 squared plus 2 gives us 3 for the first one. That checks out. A sub 2 gives me 2 squared plus 2 equals 6. That checks out. And you would do the same thing for the other ones to see that this is the rule. Okay? Another thing with sequences is, it's not a continuous function because our inputs are discrete, which means, we don't have a continuous line like in algebra or whatever when you graph y equals x squared. This was continuous because our domain was usually the real numbers. But here, our domain is the natural numbers. Okay, so we're not going to have a continuous picture like the parabola where you can draw it without picking your pencil up. So anyway, this is just a little graph I found on Google. And we have the terms in our sequence on the y-axis along with the term number on our x-axis. So just from looking at this graph, we can say that the first term, a sub 1, looks to be about, I don't really know. I would just say this is like 2 or something. Maybe that's not a great estimate, but this looks like about y equals 2. And then the second term, okay, that looks like 5. So a sub 2 is 5, and so forth. Right, we can figure out what this is. This looks like it's like 9 or something. So a sub 3 is 9. And we can keep going. But the point is that we can graph sequences. Okay. So next definition I want to talk about is an epsilon neighborhood. Okay, so you should honestly get this tattooed on you. Just kidding, but I'm gonna say it like pretty much from here on out until the end of the course, like a bunch, okay? So let epsilon be greater than 0. Okay, so that's like that's what we're gonna start out with for a lot of these proofs that we're gonna do. So what do I mean by epsilon being bigger than 0? I mean that epsilon can be any number bigger than 0. It doesn't have to be an integer or a natural number. It could be something like 1 over a trillion. Okay, I don't care what epsilon is, no matter how small it is. The only condition I'm imposing on it is that it needs to be larger than 0. Okay, so let's define what an epsilon neighborhood is. And it's kind of intuitive, what it is based on the word neighborhood. And basically, if you have a point L, okay, L could be any real number, I don't care. The open interval from L minus epsilon to L plus epsilon is the neighborhood centered at L. Okay, so maybe I'll write this. This is the neighborhood centered at L. So we can think of it like if you're looking at the real line and you're given some number L, it's going to be directly in the center of this neighborhood. So if I choose a number right here, I would say this guy lives in the epsilon neighborhood. Like, he's literally hanging out in a neighborhood. Whereas this guy does not live in the epsilon neighborhood. And if you want to, get more concrete about it, I guess, you could say, let's have L equals 2 and epsilon equals 1/2. Where's our neighborhood on our picture? So if this is 0, this is 1, this is 2. Okay, well, my epsilon neighborhood is going to be centered at 2, my 1/2 neighborhood. And I'm going to go out 1/2 to the left and 1/2 to the right. So 2 minus 1/2 is going to give me an endpoint at 1.5. Right, so this is 2 minus 1/2. And then the other endpoint is going to be at 2 plus 1/2. So 2.5, and here's 3. So that's what I mean by an epsilon neighborhood. You give me an L, you give me an epsilon, I can build a little neighborhood around it. Okay? Alright, so here's where things are starting to get serious. Okay? So I'm about to give you a definition that you really need to understand. And I'm going to say this, I'm going to say this a few times in this lecture, but I think the author says something like, if you don't understand this, brew a pot of coffee or something and like come back to it. Okay, so it's really, really important that you understand this definition thoroughly, because it's going to come up again and again and again and again. Okay, so I'm going to go through it really carefully and try to explain every single thing and what everything means. But it's on you to process this information and really understand it. And of course, I can help you in office hours, etc. But yeah, really, really think about this. Okay, so a sequence, A sub n in the parentheses, and actually I'll just write it like this without the parentheses so we get used to seeing that. I mean, it's technically like, I don't know. Is it bad practice to write it like that because it kind of looks like a term in the sequence? I don't know, but it doesn't matter. Like, the context will be clear, okay? And since I'm saying before a sequence, that means that this is not a term in a sequence, but a sequence itself, okay? So sequence A sub n converges to L in the reals if for every positive epsilon there exists some n in the naturals, so that whenever little n is bigger than capital N, the sequence is in the epsilon neighborhood of L. Okay, and it's like, what are you talking about? This is a lot of mumbo jumbo, but let's dissect what's really happening, okay? So what do you think of when you hear converge? Well, if you took Calculus 2, you know exactly what that word means mathematically, and just what it means in everyday life is you're getting closer and closer and closer to something, and you don't pull away from it at a certain point. And that's what we want to illustrate here rigorously, okay? So we have this sequence, okay? And we want to say rigorously, what does it mean for the terms in the sequence to get closer and closer to this number L, and eventually stay really close to L and never stray off, okay? We want to illustrate what this means, okay? So let's dissect this definition, okay? So this is telling me for every epsilon positive, whether that epsilon be a trillion, or whether that epsilon be 1 over a trillion, or whether that epsilon be 1 over a trillion and 1, however small you tell me that epsilon is, I'm going to give you some number so that when you hit a certain point in your sequence, everybody in the sequence is trapped in that tiny little neighborhood. Okay, so the intuition of this definition is no matter how tiny your neighborhood, aka epsilon, no matter what you choose epsilon to be, after a certain point, okay, that's where this capital N comes in. After a certain point, capital N, your sequence will stay trapped in the neighborhood, okay? And we're really going to dissect what this means, okay? So just bear with me for now. But an important note is that the N that you choose depends on your epsilon, okay? So let's go ahead and look at this picture right here that I have to the left. And I want you to really, really think about this picture. Really, really like this picture. So look at the sequence. That's the dots everywhere is the sequence. And here's A sub 1, here's A sub 2, here's A sub 3, here's A sub 4. Okay, it's kind of bouncing around a little bit. But nonetheless, we can see what's happening over time, okay? As the sequence goes on, we can see what's happening to the terms, okay? They're getting closer and closer to this L value, okay? We call that L value the limit, okay? At a certain point, these guys are going to be super close to the limit, and they're never gonna stray away from the limit, okay? So I give you this epsilon neighborhood, and the epsilon neighborhood is, let me draw it in red so that you can see it. Here's L minus epsilon. You can see the dotted line, but I'm gonna just make it red so that you can see it. So this is my epsilon neighborhood in red. Oops. Epsilon neighborhood. And so what this definition is saying, it's saying that I chose this epsilon neighborhood in red. Did this have to be the epsilon neighborhood? Could I have made it even closer to L? Could I make it even smaller? Like, yeah, I can do that, okay? But what this definition is telling me, that whatever epsilon neighborhood I choose, there is some point in the sequence so that when I go past that point, all of my terms in the sequence stay in the neighborhood, okay? Let's look at this pictorially. Okay, so if I am looking at A sub 1, this is the first term in my sequence. 1 corresponding here. That's not in my neighborhood, okay? So I cannot choose capital N equals 1 because I need every dot to be in that hood, okay? Need every dot to be in that hood. So what about capital N equals 2? Well, no, because I have this guy is outside the hood, this guy's 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 outside the hood. No. 2 doesn't work. If you look at the picture, when do all of these dots stay in the neighborhood? It happens at capital N equals 13. Okay, not capital N equals 11 because look, there's still somebody outside the neighborhood. But it happens at capital N equals 13. And so this definition is saying that when I get to capital N equals 13, anything bigger than that is going to be in my sequence. So A sub 14 is in the sequence, N is bigger, 14 is bigger than 13. A sub 15 is in the neighborhood, A sub 16, blah, 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 blah. Okay? So that's what this definition is saying. So really, make yourself a cup of coffee or tea and understand this. Okay, so the value, I'm going to keep harping on this. You're probably going to want to skip the video at some point because I'm going to really make a big deal about this, okay? So the value of capital N depends on your choice of epsilon neighborhood. Look at our picture here. If my epsilon neighborhood, forget about the red neighborhood. Forget about it. Okay, forget about the red. If I chose my epsilon neighborhood to be quite large, something like this, if this was my epsilon neighborhood, then guess what? Any capital N would work. Because look, the sequence is never leaving the neighborhood. We never have stray dots anywhere. Okay, so I can pick the smallest capital N I want. I can say, well, I'm in my definition, I'm imposing that capital N is a natural number, so we know that it has to be at least 1, and that's good enough, right? Anything after 1 is going to stay in this neighborhood. There's no stray dots anywhere, okay? So really, this is something to harp on, that the value of capital N depends on a choice of epsilon. The smaller the neighborhood, the larger capital N may have to be. Okay, now let's go back to this example. We had the original neighborhood that was in the dotted line here. Right, this was the original neighborhood centered at L. But what if I took something even smaller? What if I took my epsilon neighborhood to be this purple guy? These purple guys right here. This is my hood now. And so now I need an even bigger capital N to make sure everyone's captured. I need, let's see, do I? Yeah, because look, this guy's outside of the hood. This guy's outside of the hood. And so I need to make N at least 14, 15, 16, 17, 18. This is N equals 18. So I need N to be 18. And then past N equals 18, everybody's trapped in the hood. Okay? Everybody's in the purple hood. So let's, maybe I won't harp on this slide as much since I just gave all of that explanation, but this is going to be a nice sequence that we look at quite a bit. A sub n equals 1 over n. So this is the sequence 1, a half, a third, blah, blah, blah. Okay, and this is my a sub n graphed. Okay, so you give me, the game is, you give me an epsilon, I'll give you a capital N. That ensures that everything in the sequence past that capital N stays in the neighborhood, the epsilon neighborhood. So that's the game. So if I give you, for instance, or if you give me epsilon equals 2, okay? You give me epsilon equals 2. It's my job to produce a capital N so that the sequence stays within the epsilon neighborhood past a certain point. So if I give you epsilon equals 2, well, here's L. Here's what I'm claiming the sequence converges to, which is 0. And my epsilon neighborhood is 2, so 0 plus 2 is going to be up here. Oh, I'm going to do it in another color. Let's do it in green. Okay? So 0 plus 2 is going to be up here. 0 minus 2 is going to be down here. And I'm looking at my x-axis to see which capital N I need to pick so that everyone stays in the neighborhood. Well, it doesn't matter what capital N I pick, because you see that as we go further and further along in the sequence, a sub 12, a sub 13, a sub 14, etc., this thing is always going to stay within the green lines. This doesn't go out, and we're getting closer and closer to 0. So the point is, I can choose capital N to be whatever I want. Okay? I can choose capital N equals 1, for example. Okay? So choose capital N equals 1. Then n bigger than n implies that a sub n is still in the epsilon neighborhood. So it's saying once I go past capital N in the sequence, I'm still going to be in the epsilon neighborhood. And that's true. If capital N is 1, then when I pick a sub 2, so little n bigger than capital N, it's going to be in my epsilon neighborhood. And so is any little n bigger than capital N, a sub little n. Okay, so that's the idea here. Now, I can change it. I don't have to have the green dotted lines to be my epsilon neighborhood. Let's try this. You give me epsilon equals 1/8. Okay, now my epsilon is smaller. And I want to know what capital N do I have to pick so that all of my sequence terms stay in the neighborhood, right? So, for the big green neighborhood, that was easy. Everybody stays in that neighborhood regardless of what I choose for capital N. But now my neighborhood is between 1/8, which is going to be tiny. It's going to be like, okay, so if this is 1, this is a half. Maybe an eighth is like this. I don't know. It's like super close. Like, it's not great to draw it, but let me just pick something better. How about a 1/4? Because I want to draw it. That's all. That's all I want to do. Let's make this a 1/4. Okay, so we're choosing epsilon as a 1/4. So let's make my epsilon neighborhood around 0. So if this is a half, then a 1/4 is going to be something like this. Okay, and then the other end of this is going to be like that. Oh, shoot. Let's see. Okay, there we go. Whatever. I can't draw. You guys know this. So, just bear with me here. So there's my epsilon neighborhood with L, 0, being centered around the 1/4 neighborhood. And so the question now becomes, what do I need to choose capital N to be for all of these things to stay in that 1/4 neighborhood? Well, it can't be 1 because a member in my sequence bigger than 1, like little n bigger than 1, should imply that I stay in the neighborhood. But look, these guys are outside of it, okay? So I need to choose. Look what happens. It happens here, okay? It happens at n equals 4 when everybody just stays stuck in this neighborhood, okay? So that's why I need to choose capital N. I need to choose capital N equals 4. Then n larger than n implies that a sub n is still in the blue neighborhood. Okay, so really mull this over. Okay. Now, let's start doing some math. Okay, so here's the equivalent definition of convergence. And I think that your book gives this one first, but to me, I really like the neighborhood one because it's more intuitive for me. And hopefully that was the case. It's the case for you too. But this is the equivalent definition, and this is actually the one we're going to use in practice, okay? So it says a sequence, a sub n, is going to converge to a limit L in the reals if for every positive epsilon there exists some natural number capital N, so that whenever little n is larger than capital N, it follows that the distance, okay, I'm using that notation or that phrasing here, the distance between your sequence and the limit is less than epsilon, okay? So what does this mean in words? And we call L the limit of the sequence. What does this mean like intuitively? That means that that it's the same thing that we showed with the epsilon neighborhood, that there comes a point, we can choose a certain point if this thing converges to a limit, so that the distance from the sequence to the limit is really small, okay? So that That's where the convergence is coming in here. All right. And so my claim, and we can see from the picture here, it's pretty clear that a sub n converges to 0. Okay. And we looked at that sequence here. We can always, no matter how small my epsilon neighborhood is, of course, we are all finite beings, and I can only give you a finite picture here, but imagine if this real number extended off into numbers you couldn't even fathom that are so big. What this theorem is telling me is that I can always find a natural number so that this property holds, this convergence property holds. Okay? All right. So now I want to just talk about some notation because you'll see all of this at some point. The following are equivalent. So the sequence a sub n converges to L. This means a sub n right arrow L as n right arrow infinity. So a sub n goes to L as n goes to infinity. You might also see this without the n going to infinity, or you might see this. Okay, these all mean the same thing. Okay, so the limit as n goes to infinity of the sequence a sub n is equal to L. All right, so now I want to prove that this sequence converges to 0. Okay, and I'm going to do this very carefully for a few examples. And as we go on in the course, I'm going to get sloppy and not write every single thing because it's going to get really redundant and you're going to get bored and hate this class. So we're not going to do that. But how to approach these things is you want to do some scratch work. Okay? So what do we want? From our we're going to be using this definition over and over again, hence the 5 stars up here. Okay? So we want to find a capital N is our goal. We want to find a capital N so that this holds true. The sequence minus the limit is less than epsilon. So that's where I'm going to start, is what I have circled. Sequence minus the limit is less than epsilon. And this is just scratch work. So my sequence a sub n is 1 over n. I want this minus the limit, which we're saying is 0, to be less than epsilon. This is what we want. And we're trying to find the capital N that will do this job. Okay? So now what we're going to do is we're going to, like, whatever you call it, solve in terms of n, in terms of little n. Okay, so we have 1 over n minus 0 is simply 1 over little n. Now we can get rid of the absolute value bars because little n is a natural number. Remember, little n is a natural number, so it's always positive, so the absolute value bars are not needed. And we just have 1 over little n is less than epsilon. Now I want to solve in terms of n, so I'm just going to multiply both sides by n and divide by epsilon. And I do not have to worry about any kind of sign flipping because epsilon was assumed to be positive. Okay? We're always assuming epsilon to be a positive real number. Okay? So this is where you stop, and this is where you choose your capital N. And I'm going to do lots of examples and kind of explain the logic more, but I just want to give you the mechanical feel of this. Okay, so this is where we say, now that little n is isolated, we're going to choose capital N bigger than 1 over epsilon. Okay, so this is not the proof. This is the scratch. Now we're going to get to the actual proof. We're trying to prove convergence. So we're trying to prove, and we got to go back to this definition. We're trying to prove that you give me an epsilon, I'm going to produce a capital N so that this inequality holds true. Okay? So here's my proof. Let epsilon be bigger than 0. You give me an epsilon. Okay? Choose capital N. Actually, let me write it like this. Let me write it better. By the Archimedean property, And again, I'm going to get sloppier as time goes on, but I'm going to write it all out for now. We can choose a natural number such that, so remember what the Archimedean property said. It said, you give me a real number, I can find a natural number bigger than it, okay? And that's where this is coming from. You gave me an epsilon, guess what? I can find a natural number bigger than 1 over epsilon, okay? Any number, 1 over epsilon, okay. So we can choose capital N and N such that N is greater than 1 over epsilon, okay? All right. Then we have the following. Actually, let's write it like this. So what's missing here? We have to next say whenever, I have to say whenever little n is bigger than capital N. So I have to show that this implies this inequality. Thus, when little n is bigger than capital N, we have, okay, so we need to let little n be bigger than capital N. That's the hypothesis. We're trying to prove that implies the inequality. Okay, so we want to say, so since we're assuming little n is bigger than capital N, and we're assuming that big N is bigger than 1 over epsilon, we have n is bigger than n, which is bigger than 1 over epsilon. Okay, that's just what we have. And therefore, this tells me that little n must be bigger than 1 over epsilon. You see, this is bigger than this is bigger than this has to be bigger than this, okay? And now we just go to our scratch work and sort of work backwards. Since we have this, we have this. Since we have that, we have this. Since we have that, we have this. Okay, so like with the scratch work, we started where we wanted to get to, but when you're actually writing your proof, you want to make this the last step because you're trying to show, okay, I'm given an epsilon, I choose a capital N. That means when little n is bigger than capital N, this implies the result that I'm trying to get. Okay, that implies this. Okay. Oh, I hope I'm recording this. Okay, good. It's like, am I not recording? That would be really bad. So, this implies, when we just work backwards, 1 over n is less than epsilon. This implies that absolute value of 1 over n is less than epsilon. This implies 1 over n minus 0 is less than epsilon. And therefore, we have shown that 1 over n, sequence 1 over n, converges to 0. Okay? So just as a recap, why have we shown this? We've shown that if you give me an epsilon, I can produce a capital N. In particular, capital N is something bigger than 1 over epsilon. I don't care what it is, but I know that it has to be bigger than 1 over epsilon. And then little n bigger than capital N implies this. And we're done. So that's how we're going to structure these epsilon n proofs. And again, if this looks strange and scary, that's pretty normal if you have not seen this before. So just sit with this definition, make some coffee if you have to, and here's an outline of how you can tackle these proofs. So I'm just going to say what I just said. Basically, you're going to start with the conclusion and solve for little n, and that's going to tell you which capital N to choose. Then you're going to let n be the value of n. Well, actually, we're going to change this to say be greater than the n that you got in the scratch work. And then you're going to redo the scratch work. Okay? So, let's go ahead and do this. Okay, so here we have a sequence. Try to pause the video, see if you can get the scratch work down. So this is not the start of the proof, but I want to start with the conclusion that is the sequence that I'm given, which is 5 minus 1 over n squared, minus the limit, which I'm given as 5 is my limit. I want this to be less than epsilon, okay? And I want to figure out the capital N that'll do this. Okay, so let's go ahead and scratch work it. 5 minus 5 is 0, so this gives me negative 1 over n squared. Let me do it in red. Negative 1 over n squared is less than epsilon. Now we know that from our absolute value properties, this is the same thing as 1 over n squared. We can just pull out the minus. And because this guy's always going to be positive, I can simply remove the absolute value bars at this stage. Okay, and now I'm going to go ahead and solve for little n. So multiplying by both sides and dividing, we get little n squared is bigger than 1 over epsilon. And notice I'm not worrying about signs flipping because n squared is always going to be positive and epsilon is always going to be positive. No problems there. So when I take the square root, again, epsilon's positive, so I don't have to worry about a weird sign flip. I'm going to get that little n is greater than 1 over the square root of epsilon. Okay, and that's going to tell me what I need to choose for capital N. Okay. Now your book, I think what he does is he actually lets capital N equal this. But things can go awry when you do that in general, and so that's why I'm letting capital N be larger than this. And I can't think of an explicit example right now where things get messed up if you choose capital N to be the thing, but it does happen. So I just like to be on the safe side and choose, by the Archimedean property, choose the capital N bigger than the thing that we get. Okay. All right. So that was our scratch work. Now the start of the proof. This is our formal proof. And in your homework, you should write the formal proof with all the steps. I'm not going to ask you this after this homework. You can hand wave some things, but after this fourth homework, but I am going to ask you to write the proofs nice and, from start to finish until we get used to it. Okay, so here's the proof. What's the beginning? Get it tattooed. Let epsilon be bigger than 0. And then we're going to choose our capital N. So choose capital N bigger than 1 over root epsilon. And just in parentheses, we can do this by the Archimedean property. Oh, I know why. Okay, I just literally thought of this while I was writing. Okay. So let me explain why I'm doing the capital N is larger than and not equal to. So in your book, I believe that Cummings says that capital N can be a real number and not just a natural number, but this isn't standard. In my definition, I'm requiring capital N to be a natural number so that we can use the Archimedean property. I haven't seen, I'm sure it exists, but I haven't seen in any other analysis textbook where they let capital N be a real number. And so the reason I'm choosing capital N to be greater than 1 over root epsilon instead of equal to is because I can't always have a natural number equaling 1 over root epsilon, right? What if epsilon is something crazy like square root of 2 or something? Well, then it wouldn't make sense to have a natural number being 1 over square root of 2. That's not a thing. So that's why I'm requiring it to be strictly greater, okay, and not equal to, like your book does. Okay? Yeah, I would say that's probably my one complaint about the book so far, is that it's not standard to say capital N is a real number, I don't think. So, alright. Anyway, that was just an aside. Alright, where are we? Okay, we can do this by the arc and median property. Then we start to work backwards. Okay, then our hypothesis, we need to say n is bigger than capital N. And this implies, well, we know capital N is bigger than 1 over root epsilon. So this says we have n is bigger than n, which is bigger than 1 over root epsilon. And this implies that little n is bigger than 1 over root epsilon. And that's where we ended. And now we're going to start backtracking to end the proof. And we want to end the proof here. Okay? This is our ending. So we start backtracking and we say this implies that 1 over epsilon is bigger or less than n squared. Again, I'm not going to do this every time, but just so you guys see. Oh wait, did I screw something up? Yeah, I did. Yeah, I did screw something up right here. This should be 1 over n squared is less than epsilon. Okay. And then this is going to imply that I'm just going to skip to the top step. 5 minus 1 over n squared minus 5. And therefore, 5 minus 1 over n squared converges to 5. And that makes sense, right? As n gets really big, this whole thing goes to 0. 5 minus 0 is 5. So, alright, here's another one. And again, you can skip around. Let's see where we're at in the video. About an hour in. I'm hoping we can do everything I wanted to, but we'll see. Okay. Alright, so here's the scratch. So we want to start where we want to end and end where we start. So sequence, we want to do sequence, which is 3n plus 1 over n plus 2 in our case. Subtract off the limit, which we're claiming is 3, is my L. And we want to show that this is less than epsilon. So this is just scratch work. Alright, so here's the thing. Common denominators. We get 3n plus 1 minus 3 times n plus 2 all over n plus 2. Okay, combine the terms on the top to get... uh-oh. What is this? Ooh. Negative 3n 1 minus 6. Okay. Let's see. Yeah, I think this is... Yeah, sorry. Okay. Can't do math. I'm like looking at my... I can't do arithmetic very well these days, so I'm like looking at my notes. I'm like, wait, why is it negative 5? Oh, it's because 1 and negative 6 makes negative 5 and not 1. I was confusing myself. Okay, so that simplifies to that. And then again, by the absolute value properties, this we can pull out the negative, and this absolute value of negative 5 over n plus 2 is simply absolute of 5 over n plus 2. And since this guy is always positive, no problem with removing the absolute value bars. Okay, and now we're just trying to solve for little n. Okay, so do the thing, multiply by n plus 2. And we're trying to get little n is bigger than something. So let's go ahead and divide out by epsilon and subtract 2. Okay. All right, so now we're at the point where we can construct our proof because we know what our capital N has to be since we have little n greater than something in terms of epsilon. So the start of the proof, always the same thing, let epsilon be bigger than 0. Choose capital N in the natural numbers such that capital N is bigger than 5 over epsilon minus 2. Okay? Then, oh, and we should say, can do this by the Archimedean property. Then, n bigger than capital N. Remember, we need to incorporate that hypothesis. Implies the following. We have n bigger than capital N, which we said was bigger than 5 over epsilon minus 2. And so this means that little n is bigger than 5 over epsilon minus 2. And now we're at the point where we can start working backwards. Okay, so you want to say this line next, then this line, and then finally up to this guy. And I'm not going to say it at this point because we've already done too many examples where I said every little thing. But the idea is you're repeating the work until you get to our very first line, which is 3n plus 1 over n plus 2. Is less than epsilon. And we're done. Therefore, we have shown that this sequence does indeed converge to 3. All right, what about this one? Okay, I'm looking at the time. We're good. Okay, so we want to show the limit of this guy is 2 or 5. So yeah, try pausing the video, see if you can do this. Okay, so here's our scratch. Sequence minus limit. Here's the limit. Less than epsilon. Okay, do the thing. So subtracting on the inside is going to give us 5 times 2n plus 1 minus 2 times 5n plus 4 all over 5 times 5n plus 4. I want this less than epsilon. Okay, now we can combine like terms on top to give me, let's see, the 10 n's are canceling out, and then we get 5 minus 8, which is negative 3. I hope. Negative 3 over this. All right, again, by properties of absolute values, this was in lecture 2. This is just 3 over 5 times 5n plus 4. Okay, and so this thing is always going to be positive on the bottom. No problems with removing the absolute value bars. Don't have any issue there. And now we're just trying to solve for little n so that we can choose our capital N. Okay, so I'm going to I only see one little n, so I'm just going to distribute the little n, the 5 into this guy. So that's going to give us 25 little n plus 20 less than epsilon. And I'm going to go ahead and isolate my little n. Okay, so first multiply to give me epsilon times 25n plus 20. Again, no problem with signs. This is always positive. Okay. All right, so now I want the little n greater than something, so I'm going to move my epsilon by dividing both sides by epsilon. Then I'm going to subtract 20 from both sides. And finally, I'm going to divide everybody by 25 to get the little n is bigger than something. That's what I wanted. And 20 over 25 is 4 over 5. So I'm going to just write that like that. All right, now I know what my capital N is going to be. Okay, so here's my actual proof. Let epsilon be bigger than 0. Choose capital N such that capital N is larger than 3 over 25 epsilon minus 4 over 5. Then, and why can I do this? Archimedean property, but I didn't say it. See, I'm getting sloppier as time goes on. Okay, so then n bigger than n implies n is bigger than 3 over 25 epsilon minus 4 over 5. And this is where I'm starting to get sloppy, because now this implies this. But again, just don't do what I do on your first homework. But on the second one, I think this is okay if you skip some steps. Blah, blah, blah. And then the final step is going to be the top thing that we started with. This. And we're done. We have shown that this sequence converges to 2 over 5. Okay? All right. Now let's do a weird one. Okay? So this trick that we've been doing, this little computational, whatever, playing around that we've been doing, is not going to work for this because, try it. Let's try it. So if we start from the end goal, minus 0, that's our limit candidate. We want this less than epsilon, okay? And so we have sine of n squared over root n less than epsilon. Okay, so we have some problems here. So what do you think the problems are? Well, for one, we can't say, we know for sure that this is positive, right? This doesn't have to be positive. The sign of something could be, remember the sign of something ranges from -1 to 1, so we could have a negative value there. And also, we have too many n's involved. Like, if we were to say, okay, well, if we made this like this. So I'm showing you this to just show you what's wrong. We're trying to get little n by itself, but the problem is we can't isolate little n, right? Because we have sine of little n. We can't do this. It's getting messy. It's getting unruly. So we have to figure out a different way to proceed before we start doing the computational stuff. Okay, so we need to bound this. Okay, so we need to bound this. So what do I know about the sine function? What do I know about it? I know need to bound. What do I know about the sine function? I know that the sine of whatever is always going to be between -1 and 1. Okay, that's true. No matter what your angle is, the sine of an angle is always going to be between -1 and 1. Okay, now we also know that this is always going to be positive. Okay, and so therefore, the sine of n squared over third root of n, if I just simply divide everybody by third root of n, then I know that this guy is going to be between these guys. Okay, and I need something like that because you see, in effect, by bounding this in something purely in terms of little n, now I can start my computation again because I don't have to mess with, like, you know, like things are going to get screwed up if I have more than one little n in a term. Okay? So, what am I going to do? Well, I'm going to just start from where I would normally start. And I'm going to say, okay, I'm going to say absolute of sine of n squared over radical, or third root of n, minus 0. Okay, I said that this is going to be less than or equal to 1 over third root of n. So this is going to be less than or equal to 1 over third root of n. Okay, and now we're starting, now that we know that, we can say, okay, well, let's continue the computation and say we want this less than epsilon. Okay, and it'll all go together when, like, it'll all fall into place once we do the proof. And so now it's pretty easy to solve for little n. Now I can just multiply both sides by third root of n and divide by epsilon to give me 1 over epsilon is less than third root of n, and then I can just cube both sides to get little n alone. So this is going to be my choice of capital N. And let's see how it all fits together. Okay, so the idea, let's go back. We couldn't do this computation outright. We couldn't solve for little n outright and the inequality. So we had to bound it by something. We had to use the fact that sine's always between -1 and 1 to bound the sequence. And so, yeah, that's pretty much it. So here's the proof. Let epsilon be bigger than 0. All right, and we're going to choose capital N bigger than 1 over epsilon squared. Okay, then our hypothesis, n is bigger than n, implies the following. Okay, so we have n is bigger than 1 over epsilon squared, and this implies, I'm going to the next line, root 3n is bigger than 1 over epsilon, and I'm just continuing here, and this implies that 1 over third root n less than epsilon and what do we know? Well, we said that 1 over third root n was bigger than or equal to the function in question. So let's just write it all out. Sine n squared over third root of n. Okay, and this implies that absolute, right, because we're just looking from here to here, right? That's what we wanted. This implies that sine of n squared over third root of n minus 0 is less than epsilon. And therefore we have shown what we wanted to show, that this sequence converges to 0. Okay, so that's that. Okay, let's try another example. So let's say we have a sequence 3n cubed over n to the 4th plus 6. We want to prove that the limit of this sequence is 0. So that's our L. And so we can do some scratch work, as we usually do. So we have 3n cubed, our sequence, over n to the 4 plus 6 minus 0. We want this to be less than epsilon. And so we get 3n cubed over n to the 4 plus 6 less than epsilon. This is always positive because little n's a natural number, so we can remove the absolute value bars. And we want to get little n by itself so that we can choose what our capital N has to be. And so if I try to do that, I realize that I can't get little n is bigger than something, right? If I multiply both sides by n to the 4 plus 6, and then, like, I don't know, divide both sides by epsilon, I could get 3n cubed over epsilon bigger than n to the 4 plus 6. And then I have n to the 4 plus 6 over 3n cubed bigger than 1 over epsilon. And so I'm not getting little n greater than something. That's what I want. I don't want this n to the 4 plus 6 over 3n cubed. That's not going to give me my capital N that I need. Right? I have too many dependencies going on, I guess. So we can't do this. We need to figure out some kind of bound so that we can get little n greater than something. Right? We want little n by itself. So let's erase everything that we've done. And we're going to try to find a bound here so that we can get something simple so that we can choose our capital N in a smart way. So here's some scratch. So find a bound. We want to find a bound since we couldn't get little n isolated. Well, if we look at our sequence here, we know that on the bottom, little n is a natural number, right? And so the idea here, is that 1 over n to the 4th is always going to be larger than 1 over n to the 4th plus 6, right? We have a positive natural number, and if we add something on the bottom to our positive natural number, the resulting fraction is going to be smaller, right? It's like 1/2 is bigger than 1/3, that kind of idea. The bigger your denominator, the smaller the overall fraction is. And so here's the idea. And so what we can say, that 3n cubed over n to the 4 plus 6 is actually going to be smaller than 3n cubed over n to the 4, right? Because of this denominator. Adding something to the denominator is going to make the result smaller. That's a very, big idea that always is coming up. So now this is cool because 3n cubed over n to the 4th becomes 3 over n. And now this looks much simpler. Now we can mess around with our epsilon stuff. So if I want this to be less than epsilon, and I solve for little n, I get 3 over epsilon. Little n is bigger than 3 over epsilon. Okay, so that was the scratch work. We wanted little n bigger than something in terms of epsilon. We never want little n to be in terms of little n. I mean, that doesn't make any sense. We only want our little n to be in terms of epsilon because our big N should only depend on epsilon. Okay, so here's the proof. Let epsilon be bigger than 0. Choose capital N. We know what to choose for capital N. Choose capital N bigger than 3 over epsilon. I did epsilon over epsilon. Then, n bigger than n implies the following. 3 over epsilon smaller than n. I'm just working backwards. So this equals 3n cubed over n to the 4th, smaller than epsilon. I'll just do my imply errors. And we know that this guy, by our bound, is going to be bigger than this guy for all natural numbers. And therefore, okay, and the claim is shown. All right, so that's the idea of bounding in these epsilon n proofs. So if you can't get a little n bigger than something, like we did here, you're going to want to do some bounding tricks and argue that way. All right, so let's look at a theorem here. Okay, so the limit of a sequence is unique. We can't have a sequence converging to more than one limit, is the idea here. And so for our scratch, let's do scratch for the proof. And maybe we'll, think of what it would mean if a sequence converged to two different limits. So suppose a sequence a sub n converged to a limit a, and a sub n converged to a limit b. Well, since our sequence converges to a, we know that for any positive number, there exists some capital N. Let's call it capital N1 because we have two different situations here. So let's write it out here. What do we know? We know that since a sub n converges to a, for all, and I'm not going to write epsilon here, I'm just going to say, and maybe I'll write it out, for all positive numbers, there exists capital N1 such that a sub n minus a, or I should say n bigger than n1, implies that absolute value of a sub n minus a is going to be less than the real number that we choose. Okay? And same thing for the sequence converging to b. So same thing for all positive numbers, there exists a separate value, capital N2, so that whenever little n is bigger than capital N2, this implies that the sequence minus b is going to be in that neighborhood. Okay, and so the idea here is we're going to use the triangle inequality, right? Because maybe it's, I want to give you the intuition for what I'm doing here. So let me just write this off to the side. What do we want? We want to show that the limit, if it exists, is unique. So we want to claim that, or rather, we want to conclude that A equals B. Okay, so like we said, all right, let's let our sequence converge to two things. Let it converge to A and let it converge to B. And I want to show at the end that A actually equals B. And so this is where my thinking is. This is why I'm gonna set it up as I do, because I want to show that the absolute value of A minus B is equal to 0. Okay, that's what it means for A to equal B. Remember those properties of absolute value? The difference of two numbers is equal to 0. So I want this, and if I write A minus B in a sneaky way to involve my sequence, right? I'm trying to involve things that I have, and I'm trying to involve my sequence somewhere. So if I write A minus B in a sneaky way to involve my sequence, right? I always want to use what I have somehow, and that's my sequence. So again, this is our goal here. Let's see, maybe I'll just box it like this. Okay, and how am I going to sneakily write A minus B involving A sub n? Well, triangle inequality. I'm going to write A minus A sub n plus A sub n minus B. And this is the same thing as A minus B. These cancel, right? And so I'm going to use a triangle inequality to say that this is less than or equal to, well, this absolute value of this term plus absolute value of this term, right? And you can, it takes practice to see this, but after you do this for a while, you start to get used to it. But it does take practice to see what to do. And hopefully this intuition helped. Like, okay, I'm trying to get A minus B equals 0. And so I want to also bring in the A sub n because I have it. And the way to write A minus B in terms of A sub n is like this. I can use the triangle inequality, and this is great because if I look upstairs, I know that what it means for A sub n to converge to A is exactly this, and what it means for A sub n to converge to B is exactly this. And so I'm also going to write this guy by just saying this is equivalent to this, right? I'm just going to use the negative value of the absolute value to say that this is equal to this. Okay, so I'm just going to switch it, do a switcheroo so it looks like things that I have. All right, this is equal to this. Okay. Okay, so now I know I'm in good territory because I'm using what I have to conclude something. Now, what do I want? I want this to be equal to 0, okay? And I'm letting my epsilon be a number bigger than 0, but I can let it get as close as I want to 0. So as long as this is going to epsilon getting really close to 0, then I'll have what I want. Okay, so the idea here is that I want this to be less than epsilon, where epsilon goes to 0 from the right because epsilon's positive. Okay, so that's the idea. Now, if I want this to be epsilon, I need to make sure this is epsilon over 2 and epsilon over 2, right? epsilon over 2 plus epsilon over 2 is epsilon. Right? I'm trying to make this so that I get absolute value of a minus b is less than epsilon, and then letting epsilon go to 0. This is going to give me that a minus b equals 0. Hence, a equals b. All right, so I want this to be epsilon, and so the whole thing being epsilon means that I can make this epsilon over 2, and I can make the second absolute value epsilon over 2 to give me epsilon. Okay, so this is all scratch work. This is all how you should be thinking about how to prove something like this. So the idea here is, how do I make this be epsilon over 2? How do I make this be epsilon over 2? Well, here's what we're going to do formally. So here's the start of our proof. So we're going to let epsilon be bigger than 0. And since an converges to a, and an also converges to b, there exists a capital N1 so that little n larger than n1 implies a sub n minus a is less than epsilon over 2. Okay? Right? Can this epsilon over 2, I'm choosing this based on this, right? There's always going to be a natural number that I can choose so that if I go down far enough in my sequence, the distance between the limit and the sequence is going to be smaller than epsilon over 2. Could be epsilon over 3, could be 100, could be whatever. But as long as it's a positive real number, I'm good. Okay? It doesn't just have to be epsilon. It just needs to be a positive real number. Okay, so similarly, since, well, actually, maybe I should have just said it like this. I should have said, let epsilon be bigger than 0. Since a sub n converges to a, there exists an n1 so that this is true. And then I'll say, similarly, since a sub n converges to b, there exists a capital N2 so that little n bigger than capital N2 implies that distance between a sub n and b is less than epsilon over 2, right? I'm trying to fill in the details here. Okay, so this is just definition of what does it mean to converge. So now what we're going to do is we want both of these things to be true simultaneously. And the way to do that is to choose a capital N for the whole thing that is the max of capital N1 and capital N2, because if I'm picking something that is bigger than or equal to both of these, then the implication will follow naturally from that. So let me show you what I mean, okay? Choose capital N is equal to the max of N1 and 2. Okay, the maximum of these is going to be capital N. Then, n bigger than capital N, what does that mean? Well, since capital N is the max, if little n is bigger than capital N, we have little n is going to be bigger than n1, and little n is going to be bigger than n2. Right? Both of these things are true if n is bigger than the max of n1 and n2. Okay? Because the other one's, like, If n1 is bigger, then n2 is going to be the smaller thing. So if little n is bigger than n1, it's certainly going to be bigger than n2. So both of these things are true at the same time. And that means that these inequalities hold. Both of these hold simultaneously. All right? So we have the following. Okay, now comes our scratch work, right? We started here, right? So we have a minus b is equal to, a minus a sub n, and then minus b plus 8, or let me just write it like this. Okay, so that equals that, just by being sneaky. And so by the triangle inequality, this is the triangle inequality, this is going to be less than or equal to the absolute value of the terms. Okay, and this is equal to, let's see, it's not, is it going to let me go down anymore? No, it's not going to let me go down anymore, but this is going to be equal to a sub n minus a plus a sub n minus b, just based on our properties of absolute values. And we already said that because I chose capital N so that it was the max of n1 and n2, that means that both of these things are true simultaneously, which means that this guy is less than epsilon over 2, and this guy is also less than epsilon over 2. So this is going to be less than epsilon over 2 plus epsilon over 2, which equals epsilon. Okay, and I'm running out of room, so I'm going to write the rest up here. Remember, epsilon was arbitrary, so we can let epsilon go to 0 from the right. We get our desired result. We get that absolute value of a minus b is equal to 0, and hence a equals b, and so the limit is unique. Okay, so the next theorem we're going to talk about are the limit laws that you probably learned in Calc 1. And so basically, if you have two sequences, a sub n and b sub n, and a sub n converges to a real number a, b sub n converges to a real number b, then the following 5 things hold. So if you take the sum of the sequences, then that sequence is going to converge to a plus b. The difference is going to converge to what you expect, a minus b. Multiplication converges to a times b. And same thing with division, but you can't have b equaling 0 or b sub n being 0 because of denominator restrictions. And then if c is a real number, then c times a sub n is going to converge to c times a, because a sub n converges to a. So I think I'm going to prove number 3 at the end of the video if we have time. If not, I will refer you to the textbook, but let's go ahead and move forward and come back to the proof of limit law 3. Okay, so the next thing we need to learn is the squeeze theorem for sequences. So if you have a sequence that is nested between two other sequences, so all of the terms in your sequences are bounded above and below by terms in other sequences, like x sub 1 is bigger than or equal to a sub 1 and less than or equal to b sub 1, and so forth for all n. And if we assume that the leftmost sequence converges to L and also the rightmost sequence converges to L, then the middle sequence is forced to converge to L. I'm going to refer you to the textbook for this proof, but let's go ahead and do an example, see this in action. So typically you want to try and employ the squeeze theorem if you have a really complicated limit that is not simple to prove that the limit exists with the convergence theorem. So here I have this crazy looking fraction, and I'm trying to prove that the limit of this sequence as n goes to infinity is actually 0. Okay, so the idea here is to sandwich this sequence between two other sequences that we know the limit of. Then by the squeeze theorem, we'll know the limit of the middle sequence, this big weird thing. So what is this guy less than or equal to? Can you think of a sequence that that this guy is going to be smaller than or equal to? Well, look at the denominator. Okay, the denominator is always going to be a positive number because little n is a natural number, hence always positive. And so this guy is always going to be smaller than or equal to 1 over n, right? The smaller the denominator is, the bigger the actual fraction is. So this thing is bigger than this thing. Okay? And we know that this is always going to be positive, and so I can definitely say that this is always going to be bigger than or equal to 1 over n. Now, I didn't prove that this thing goes to 0, but you can see it pretty easily if you follow the steps that we used to show that this guy went to 0. So this guy goes to 0, and this guy goes to 0, and so by the squeeze theorem, this guy has to go to 0. I kind of like the sandwich theorem better than the squeeze theorem, but you can call it whatever you want. Okay, so the idea is we found two sequences that sandwiched it, and both of those sequences went to 0, forcing the middle one to go to 0. Okay, so not every sequence converges. We have some sequences go off to infinity, some go off to negative infinity, and some just do not have a limit. Okay, so we're going to talk about these three cases. So the first case is that if our sequence diverges off to infinity, and the notation that we use is this guy, limit as n goes to infinity of the sequence equals infinity, and the way that we can prove this is that for every real number, m bigger than 0, if there exists, I don't have it here, but if there exists capital N in n, such that whenever little n is bigger than capital N, this implies that the term in the sequence is bigger than m. And so what that means intuitively is that you can always find something bigger in your sequence than any positive real number, right? So if I give you 200 million, I can always find something in my sequence bigger than that, okay? And how do we prove this? The same way that we did the other convergence proofs. So we start with what we want, which is our sequence being bigger than m, that's given. So our sequence in this case is a sub n equals 2n, so 2n greater than m, and we solve for little n. So we get little n is bigger than m over 2, and that's all we need to do to choose capital N. So for our proof, we let m bigger than 0 be given, just like with the epsilons. And then we choose capital N bigger than m over 2. Then little n bigger than capital N implies that little n is bigger than m over 2, and hence 2n is bigger than m. Okay? So, you can think about it like if I give you m is equal to 100, you can choose your capital N to be bigger than 100 over 2, which is 50. So if I choose capital N equals 51, this should all work out. Then 2 times, so whenever little n is bigger than capital N, if I look at the 51th term in my sequence, I get 2 times 51 should be bigger than m. And indeed, this is true. Okay, so that's how I can, this is how I can choose my capital N. Okay, so that's in my boxed thing is my proof. This is just illustrating some scratch work. But yeah, that's what it means to diverge off to infinity. So, you know, as little n gets bigger and bigger as the sequence goes on, it's never going to converge to a single number. It's always getting bigger and bigger. And we can give an analogous statement for diverging off to negative infinity. So here is an example of a sequence that goes off to negative infinity, negative 2n. And so this is the analogous notation. And so this definition says that if you give me a negative, that was the word I'm looking for. It's been a long day. A negative real number, no matter how negative your number is, like no matter how small the number is, I can always find a capital N such that whenever I go along far enough in my sequence, I can guarantee you that there's going to be a number in my sequence smaller than the m that you gave me to begin with. Okay, so that's what it means to diverge to negative infinity. Okay, also there's another option where you can have a sequence diverge, but it doesn't go off to positive or negative infinity. It can also diverge if the limit does not exist. So for example, our sequence a sub n equals negative 1 to the n is going to oscillate between positive 1 and negative 1, depending on whether little n is whether little n is even or odd. So when little n is odd, you're going to get negative 1. When little n is even, you're going to get positive 1. And so your picture of your sequence kind of looks like this, and you can see that these values are never converging to a common value here. And so let's go ahead and prove that this guy diverges. And so we're going to do a proof by contradiction. So our proof by contradiction, we're going to suppose that a sub n converges to something. Okay, so we're going to suppose that it converges and then show that this is absurd. So what does that mean? By the definition of convergence, what do we have? We know that for all epsilon bigger than 0, there exists some n in the natural numbers such that when I go far along in my sequence, so little n is bigger than capital N, this implies that our sequence, the distance between our sequence and the limit, should get arbitrarily small. Okay, so that's just the definition of convergence. So for all epsilon, okay, including epsilon equals 1/2. So this should hold for epsilon equals 1/2. Therefore, we can let epsilon equal 1/2. Then there exists some n prime in n such that little n bigger than n prime implies negative 1 to the n minus L is going to be less than 1/2. Okay, so here's the issue. The issue is that this, whatever's in the parentheses, since, like this this is constantly going to be oscillating between 1 and -1 for no matter how big our capital N is. Okay, and so we have two cases to worry about. So the first case is when little n is even, right? Because we're going to get two different things inside the absolute value bar depending whether or not little n is even or odd. Okay, so in the first case, when little n is even, we get that this guy becomes +1 minus L, less than a half. Okay, and now I'm just going to use my properties of absolute values from lecture 2 and say that this means 1 minus L is going to be between a half and -a half. Okay, and then I'm just going to subtract 1 from everybody and isolate L. And so what I end up getting when I subtract 1 and divide by the negative is I end up getting that L is between a half and 3/2. Okay? My second case is going to be when n is odd. Okay, so when n is odd, inside here I'm going to get -1. So I'm going to get -1 minus L, less than a half. And doing the same sort of thing, taking this out of the absolute value bars, I get -1 minus L is between a half and -a half. And this time, when I isolate L in the middle, I get that L is between -a half and -3/2. So I get these two things, and this is a contradiction because remember, limits are unique. We proved this. And so if I have my limit, so for this first case, my limit is going to be between a half and 3/2. Here's L. And I also have my limit in between -3/2 and -1/2 from the second case. So this can't be true. These two things cannot be true, and so we have a contradiction, and therefore -1 to the n is going to diverge. Okay? All right, so the last kind of topic that I want to talk about here is bounded sequences. What does it mean for a sequence to be bounded? We're gonna talk quite a bit about this, and so it's just what you think it means, just like bounded sets. A sequence is bounded if there exists a number, m is bigger than 0, such that the absolute value of a sub n is less than or equal to m for all n and n. Now, your book doesn't list this as the official definition. It lists it as a proposition coming from the definition, but we're just going to take this to be the definition. And so what this means, this a sub n is less than or equal to m. So that means, by property of absolute values, this guy is going to be between m and -m. And so what this means geometrically is that we can always find an interval between -m and m that contains every term in the sequence, okay? So for all little n, for every term in the sequence is going to live between the real numbers -m and m. So if we look at this example here, here's just a few terms in a sequence, we could say that, I don't know, we could just say that this is -m, and maybe I didn't draw it the best, but let's draw it better. Let's say that this, okay, I'll just use the dotted line. That's m, and let's just say that this is -m. And so my sequence is going to be completely contained in between those two real numbers. So that's what bounded means. So here's two examples of bounded sequences. So the first one is a sub n equals -1 to the n times 1 over n. We could start listing out the elements in the sequence. When n equals 1, This is going to give us -1. When n equals 2, this is going to give us a half. And then it, this guy goes between -1 and 1. So this is going to give us a -1/3 and a 1/4, etc. And so we can see what's happening here. We know that this guy is bounded. I mean, this guy oscillates between -1 and 1, and this guy is going to 0, so that thing's bounded as well. And so what we can say in general is that the absolute value of this guy is going to be less than or equal to 1. We can see that the absolute value of all of these terms is less than or equal to 1. So a sub n is bounded. Okay, and then similar idea here. We know that that sine is going to be between -1 and 1, right? And so we know that sine of n, sine function, is going to be less than or equal to 1, but bigger than or equal to -1. And if we add 2, that means that sine of n plus 2 is bigger than or equal to 1. So bigger than or equal to 1 and less than or equal to 3. So this means that since this sequence is between 1 and 3, then the absolute value is certainly going to be less than or equal to 3. And so, I mean, you can see it either way, that it's bounded because it's trapped between these two numbers, or you can see that the absolute value of this sequence is going to be less than or equal to 3, and so b sub n is bounded. Okay, so here's a theorem. If your sequence is convergent, then the sequence is bounded, but not the other way around, right? So bounded, convergence does imply bounded, but bounded does not imply convergence, as we saw with our -1 to the n example. And for the proof, I am going to refer you to the book. But I want to go ahead and go back to, now that we know about this theorem and what boundedness is, I want to go back to that limit law 3. Okay, so I want to prove this limit law, and that was this guy, that if a sub n converges to a, b sub n converges to b, then the product of the sequences converges to the product of the limits. So let's go ahead and show this. So we want to show, this is scratch work. We want to show that a sub n, b sub n converges to a times b. And so we want to prove this by using our convergence stuff. And so we know, let's use what we know to build our proof. We know that a sub n converges to a. We know that b sub n converges to b. And so what we know is that we can choose a capital N. Do this in red. So there exists some n1 such that n bigger than n1 implies that the difference is less than epsilon 1. And similarly, for the b sub n case, there exists some n2 such that little n bigger than n2 implies that b sub n minus b is less than epsilon 2. So we somehow want to incorporate these things in our proof. And the question is how? Well, let's start with what we're trying to show. So we want to show that an bn minus ab is less than epsilon. And somehow we want to incorporate this stuff. And so we're going to use the old triangle inequality trick, right? So I'm going to do that by rewriting an bn minus ab as something that involves this stuff in purple. And so I'm going to say this is the same thing as AN BN minus ABN plus ABN minus AB. And the reason I'm using this as the thing that I'm subtracting and adding off is because I'm noticing here, if I factor out a B sub n, I get A sub n minus A. And over here, if I factor out an A, I get B sub n minus B. Okay, so sneaky stuff here. We're doing really sneaky stuff. But this is how you can think about it. Okay, so notice that here I can pull out the B sub n well, actually let's do the triangle inequality first to show how this fits together. So again, I'm taking this in parentheses as one term, this right here is another term, and by the triangle inequality, let's put it right here. And again, we're just trying to do some scratch work to figure out what my capital N needs to be. That's really the name of the game here. What does capital N have to be? So by the triangle inequality, this is going to be less than or equal to abs AN BN minus ABN plus abs ABN minus AB. Okay, I'm just using the triangle inequality with these two things in parentheses here. All right, so now what I'm going to do is I'm going to do my factoring trick because I'm trying to incorporate this stuff, right? I know things about this stuff, and so I'm trying to use that to my advantage. So I'll go ahead and factor out a B sub n from here. So this is AN minus A. And then over here, I'll factor out an A. And now I'm like, okay, I'm doing something right because I have the B sub n minus B. And I have the A sub n minus A. So I'm like, okay, on the right track. So I'm going to go ahead and do what you naturally would, which is pull out the B sub n and the A. So I'm going to pull out abs B sub n. Remember, by properties of absolute value, we can separate the products out in this way. Plus, now I'm going to factor out the A plus B sub n minus B. Okay. So remember, I'm just trying to see, like, what does this have to be so that this whole thing is epsilon, okay? And what do I know? Well, I know that this guy, I can choose a capital N so that this is less than epsilon over 1, this is less than epsilon over 2. And I also know something about B sub n, right? I know that B sub n is convergent. Okay, so this is what I'm going to write off to the side. Since B sub n is convergent, it converges to B. By the theorem that we just looked at, it's bounded. B sub n is bounded. And so what does that mean? So there exists some positive C for which absolute value of B sub n is less than or equal to C. Okay? So since I know that, I can just go ahead and replace abs B sub n with capital C. So this is going to be less than or equal to capital C, just replacing that there, times A sub n minus A plus abs A, which is going to be some constant. We know that little a is the limit of A sub n, so we don't have to, mess with anything there. B sub n minus B. Okay? And we know from the scratch work up here that this guy is less than epsilon over 1, and this guy is less than epsilon 2. And so we can say that this is all still scratch work. I'm trying to figure out what my capital N needs to be, right? So this is going to be less than C times epsilon sub 1 plus A times epsilon sub 2. And remember, okay, I started with what I wanted. I want this to eventually condense down to epsilon. So let's go ahead and take a look at this. I want this. Let's do an intermission. I want this to be epsilon. To be epsilon. And I have control over epsilon 1 and epsilon 2. Remember, the convergence of A sub n and B sub n means that I can choose epsilon 1 and epsilon 2 as whatever I want. I have control over these things. I don't have control over little a because that's what A sub n converged to. I don't have control over capital C because that's what B sub n is bounded by. Okay, but I do have control over epsilon 1 and epsilon 2. And so I'm going to do some scratch work to figure out what these values need to be. So again, I want C times epsilon sub 1 to equal, in a way, or whatever, equal epsilon over 2. And I want absolute A times epsilon sub 2 to equal epsilon over 2, right? Because when I add these guys, I want to get epsilon. Like, that was the whole freaking goal of the proof, okay? So I know it's a lot of stuff, you can get lost in the minutia, yada yada, but, when you practice this again and again, it'll become second nature. So even if it looks weird at first, just keep hacking away at it. Okay, so we have these two things, and so how about I just let epsilon 1 equal epsilon over 2c, and epsilon 2 equal epsilon over 2 absolute A. Okay, so there's a problem here, right? The problem is that I want this to be less than epsilon, and I'm not guaranteed that that will happen right here. Or I want it to be less than epsilon over 2, rather. And that's not guaranteed here. I mean, suppose little c, or capital C is equal to 1/2, then we get epsilon over 1, which is epsilon, and that's not less than epsilon over 2. So to remedy this, and maybe I'll just write it up here as scratch. So want this less than epsilon over 2, right? So to remedy this, I'm going to stick a +1 in the denominator, right? In that case, this will always be less than epsilon over 2. And the same thing over here. You don't want to have an issue with your denominator being 0, so I can add 1 to this and ensure that that this is less than epsilon over 2. And so in any case, we have, we're going to have this guy. Let's see, let me write it up here maybe. In any case, this guy is going to be less than epsilon over 2 if we choose our E sub 1 as follows. This is going to be less than epsilon over 2, and so is this from how we're choosing our E sub 2. And that's going to give us epsilon. Okay, so that's kind of the scratch work behind it. You can write out the formal proof by, just basically taking everything we did and going backwards. You're going to let epsilon be bigger than 0 and choose this guy as epsilon sub 1, this guy as epsilon sub 2, and then you should end up with what you want. So let's see. Should we do this? Why not? Okay, so I'm running out of room here, but let's put it all together. Okay. All right, so we looked at the scratch. Now let's do the entire proof. Oops. Hopefully that didn't mess up the video. Let's see. I think we're still good. Okay, perfect. All right, so here's the proof. We're going to let epsilon be bigger than 0. And we're going to choose capital N1 in the natural numbers so that, well, actually, here's what we're going to do instead. Let's start it like this. Yeah, let's just start with the epsilon. Okay, let epsilon be bigger than 0. Since an converges to A, there exists some n1 such that for all epsilon 1 bigger than 0, n bigger than n1 implies that a sub n minus a is less than epsilon over 2. Similarly, since b sub n converges to b, there exists some capital N2 such that for all epsilon sub 2 bigger than 0, n bigger than capital N2 implies that b sub n minus b, I should have made this an epsilon 1, and this is going to be less than epsilon 2. Also, b sub n is convergent, hence bounded. So there exists some positive real number c such that absolute b sub n is less than or equal to c for all n. Okay, so we have the setup now. Let's go ahead and say what we want epsilon sub 1 and epsilon sub 2 to be. Okay, so consider epsilon 1 is equal to epsilon over 2c plus 1, and epsilon 2 equal to epsilon over 2 absolute A plus 1. And now we need to choose a capital N, okay, because we don't know that both of these statements are going to simultaneously hold, that this guy holds and this guy holds, but we can guarantee that both of them hold by choosing a capital N large enough so that they're both true. And that is, again, going back to the max idea. We're going to choose capital N as the max of capital N1 and N2. And that way, N bigger than capital N is going to imply that N is bigger than N1 and N is bigger than N2. And since both of these things are true, that means that both of these statements will hold, and we can use them in our triangle inequality proof. Okay, so we've chosen our capital N. Now comes the triangle inequality. We have a sub n, b sub n, minus ab, remember we're trying to show this is less than epsilon, is equal to, remember our trick from the scratch work, by the triangle inequality, we have this. by our properties of absolute value, we can pull out our respective things, factor out our respective things. Okay, and remember this is bounded, so that's less than or equal to c. This guy is going to be, remember we talked about this is going to be less than epsilon sub 1, this is going to be less than epsilon sub 2. And so putting it all together, this is going to be equal to, well, actually, let's just say that this is less than or equal to c times a sub n minus a plus a, just because I'll put in parentheses, bn is bounded. Okay, that's why that's true. And this is going to be less than c times epsilon over 2c plus 1. That was our definition of epsilon 1, so I'm just using the fact that this is less than epsilon 1 here, plus a times epsilon over 2 absolute a plus 1. And using what we garnered from the scratch work, this is less than epsilon over 2, this is less than epsilon over 2, so this is going to be less than epsilon over 2 plus epsilon over 2, which equals epsilon. Okay, and we are done with this proof. And that is all I have for you guys. Thank you for watching, and I'll see you guys next time.